Hello everyone, myself Anurag Dubey, and today I am going to explain the project title on Synchronous FIFO design and verification. Before starting this project, let me give the brief overview of our projects. So first of all, we will see the FIFO mechanism working of our FIFO. After that, we will see the block diagram of our design. After that, we will cover the descriptions of our designs, design specifications, and input and output ports, their descriptions, and after that we will cover the comprehensive test plans. There are some key test cases and some advanced test cases. After that we will cover the design parts and test bench which is implemented in Verilog, and after that we will see the verifications through the waveforms and how the various test cases are executed. So let's start. So this slide explains the FIFO mechanism. So before going through the projects, first of all understands what the FIFO is. FIFO is basically a first in first out queue where data is written and read. On the basis of clocks that we are using in our designs, FIFO is classified into two parts. First one is asynchronous FIFO and second one is synchronous FIFO. Asynchronous FIFO uses two different clocks for write and read operations. Synchronous FIFO uses same clock for read and write operations. So synchronous FIFO is commonly used in digital systems for buffering and managing data flow between two modules operating at the same clock but with different read and write timings. Now to understand the functionality of FIFO, let's understand it with this block diagrams. So here we are performing two operations, write and read. In write operations, the data are written in the FIFO in a sequential manner. So first of all we are writing 4. After that we are writing 8. After that we are writing 6 in the FIFO. Now when the read operations is performed, the reading of data from the FIFO is done in the same order in which the data is written. So first of all 4 will be the read out, after that 8 and after that 6. So this diagram basically depicts the behavior of the FIFO and implementing first in first out characteristic. Now let us see the block diagram of our FIFO. The left hand side pins are the input pins which is connected to our design. So our input pins are clock which is synchronous for and which is used for synchronizing purpose, and it is the same clock which is used for reading and writing operation. After that reset signal, D in signal, write enable signal and read enable signal. In the later part we will see the descriptions of each of these pin details. In the right hand side we have three output ports which are D out, and we have two status flags which are output to the FIFO which are full and empty. Now we will see the design specification of our project. The synchronous FIFO design follows a structured and efficient approach to enable seamless data buffering. Now the module that we are using in our design is synchronous FIFO. Its description and behavior we have seen earlier, and also we are using two parameters in our design which are width and the depth. So instead of providing the hard-coded value, we are using parameters here, and it could be modified as per the need. Now let us see the various input and output ports that we have seen in our block diagrams and their description. Clock, it is basically used for the synchronizing operations. Reset signal to initialize the FIFO. D in signal, data input signal which is written in the FIFO. Write enable signal, when it is high data is written. Read enable signal, when it is high data is read. D out signal, data output which is read from the FIFO. Full and empty are the status flag. Full is set high when the FIFO is full, empty is set high when the FIFO is empty. Now let us understand the test plans which we will be covering in our design. So our test plan is broadly classified into three categories: functional test, stress test, reset and duration test. Functional test is used to verify the FIFO's basic operations like write operation, read operations, full and empty conditions. And through stress test, we verify the extreme conditions and corner cases of our design like wraparound test, simultaneous test, overflow and underflow test. And after that, reset and duration test. Through reset test, We will validate our design that the proper initialization of FIFO occurs on providing the reset signals. So these are the broad classification of our test plans. Now let us see the key test cases that we are going to execute in our design. First one is write operations, which is used to write a single data in the FIFO. After that, read operation to read the data from the FIFO. After that, full condition test. Through full condition test, we will validate the working of our full flag. Similarly, through empty condition test, we will see the working of our empty flag, whether it is properly set or not when our FIFO is empty. Single element write read test. After that, multiple write test without reading, and after the multiple reading of the data which is written in the FIFO. After that, reset functionality is test so as to check whether the proper initialization of the FIFO occurs or not. Apart from key test cases, there are some advanced test cases that we will be verifying through our test bench. First one is wraparound test. Through wraparound test, we will see the validation in data integrity after the pointer rollovers. And through wraparound test, we will ensure that the FIFO correctly wraps the pointer when the FIFO reaches the maximum capacity. That is, basically through wraparound test, we will ensure the circular behavior of the FIFO. After that, simultaneous read-write test. Through this test, we will check the FIFO behavior under concurrent read and write operations. After that, overflow handling test. Through this test, we will ensure that the FIFO buffer properly handles the data when it is full and ignores writes operations further. Similarly, through underflow test, we will validate that the FIFO behaves correctly when attempting to read from an empty buffer and preventing the invalid data access. So these are the key test cases that we will validate and implement in our design. Now, the overview of our project has been completed. It comprising of the FIFO mechanism, pin details, design specification, and the test cases. Now we will move to the design part in Verilog SDL, and to verify this design, we will see a proper test cases, and also we will generate the waveform and validate each and every test cases. Let's see the design code for Synchronous FIFO. Here we are using EDA tool for simulating our design and Verilog HDL to write our code. So let's see the code line by line. So first of all, we are declaring a Verilog module named Synchronous FIFO. It uses two parameters, width and depth, which width specifies the bit width of each data word in the FIFO, and depth specifies the number of entries that can be stored in the FIFO. After that, we are specifying the input and output ports of our designs. These inputs and output ports we have already seen in our block diagrams, which are clock, reset, data in, write enable, and read enable, and three output ports, D out, full, and empty. After that, we are defining the memory and the pointers. Through these lines, we are declaring an array which is representing a FIFO memory of size depth, where each element is width bit wide. Which we are providing here, it is width bit wides. After that, there are two pointers that we are using in our design, which are write pointers and read pointers. Write pointers tracks the write position, and read pointer tracks the read position. After that, we are using a variable named count here, which keeps track of the number of elements in the FIFO. And here we are using extra bit here, which prevents the overflow. After that, let's see the reset logic of our code. Here, reset logic is triggered on the rising edge of the clock or the falling edge of the reset. Here we are providing asynchronous reset. You could also provide synchronous reset in your design as per your need. So as we know, whenever the reset is triggered, it initializes the FIFO. So we are initializing our FIFO whenever the reset is triggered. So read pointer, write pointer, count, and D out all gets initialized. when the reset is triggered. After that, we will be doing the write operation. So the condition for which the write operation is done is that the write enable should be high and the FIFO should not be full. So we have provided this condition here. When this condition occur, then the writing in the FIFO is done, and the data that we are writing in the FIFO is D in, and the location at which we are writing is write pointer. After writing it, the write pointer increases sequentially, and the count that we are using here also gets increases. So in this way, the write operations is performed. After that, we are doing the read operation. So read operation will happen only when the read enable signal is active and the FIFO is not empty. So when this condition is satisfied, the data which is written at this location, at the location of read pointer, is read out and stored in the D out. And when the data is read, the read pointer increases sequentially by one location, and the count is decreased, because whenever we are reading from the FIFO, the number of elements get decreases. So count logic decreased here, and in case of writing operation, the count is increased. So these are the write and read operations, and the Verilog codes which are implementing it. After that, for the status flags, we are using assign statements. So for full condition to be active, the logic is that whenever my count logics becomes equal to my FIFO depth, the full flag is set high, which indicates that extra data cannot be written in the FIFO. And when my count logic becomes 0, it will indicate that the FIFO is empty, and now we cannot read any data from the FIFO. So this code basically describes the working of FIFO. So from beginning, we see the module declarations, parameters, input and output port declaration, memory and pointers, how they are declared, reset logics, write and read operations, and the status flags. So this is basically the design part of our projects. Now we will see the test bench part. Now let's see the Verilog code of our FIFO test bench. So here, first of all, I have defined a module. After that, I have set the parameters for width and depth. After that, the registers and wires are declared. The ports which were input in my designs are declared as reg here, and the ports which were output there is declared as wire here. I have also declared a variable named test case which stores the test case number. Here we are passing our test case through command line. So for that we are using a variable named test case. After that, we have instantiated our FIFO module. Now here clock is generated. This is clock generating logic. After that, dump file and dump words system task is used for simulation analysis and waveform dumping. Now I am using a system function $value plus arg to provide the test case number and to execute our test cases from the command lines. So it basically reads the test case from command line arguments, and if no test case is provided, it displays an error and stops the simulation. Here initialization for reset and write enable read enable signals is done. Now these are the number of test cases which are generated and verified. So this is the test case execution, and these are the test case numbers, and for executing any test cases we will provide it through the command line. Now let's see the logic behind all the test cases. So first one is test case for write operation. Here we are trying to write a data by enabling the write enable signal, and if the write operation is done properly, it throws the message data written to FIFO correctly, otherwise error occurs. After that, we are doing the read operations. Similarly, read enable signal is set high here and data is read out. After that, we are checking for the full condition test. Here, if the full flag is properly set, then the full condition test case is passed, otherwise it throws error. Similarly, the test case for empty conditions is done, and if the FIFO properly get emptied after reading operation, then our test case is passed. After that, there is test case for single element write and read. Here we are writing single element, after that reading it, and after that we are matching the data. Now the test case for multiple writes, we are writing multiple data in the FIFO and verifying it whether it's executed properly or not. After that, we have test case for multiple read. We are reading the multiple data which are written in the FIFO. Now test case for wraparound condition. Through wraparound conditions, we check for the circular buffer operations. FIFO properly wraps around after reaching the maximum capacity. So we will verify through this test case logic. After that, test case for simultaneous read and write operations. Here both the write and read enabled signals are set high, and we will check whether the data is properly written or read from the FIFO or not. After that, reset test case. On providing the reset test case, we will check whether the FIFO get emptied or not, because empty signals initializes the FIFO, means FIFO gets emptied. After that, test case for overflow. That is, if the FIFO is full and we are trying to write the extra data, it should throws an error and displays FIFO is overflow, means it should properly handles the extra data that we are writing in the FIFO. Similarly, test case for underflow. That is, we are reading a single element from the empty FIFO, so it should properly handles it. So this is a test case for underflow. So these are the test cases logic that we are executing in our test benches and passing all the test cases through the command line. Next, we will see how the test cases are passed through the command lines and how we could verify it from the console and the waveform. We have successfully seen the design part and the test bench of our FIFO. Now we will pass our test case through the command line and we will verify it from the console and the waveform. So here I am not generating waveform. First, let's verify from the console. So here from the command line I am passing the test case. So we have total 12 cases. So let's say first I am passing the test case 1, and test case 1 was write operation. So I am passing the test case 1 and let's run it. So here we obtained that the data written to FIFO correctly, means it correctly executes the test case, and it also verifies that my test case 1 is passed. Similarly, if we want to execute any other test case, let's say test case number 5, now run it. Here test case 5 is executed and it is giving the message single element matched. So our test case number 5 was single element write and read. Check it from here. Test case number 5 was single element write and read. So it is correctly throwing the message. Similarly, if I want to pass any other test case, let's say test case number 8, and I am running it. Test case 8 was wraparound. Now let's see what it displays. So it is displaying wraparound test case pass. So it is correctly generating the output logic on providing the test cases to the console. Now we will verify it from the waveform. Now I am generating the waveform also and will verify the test case. Let's say I am passing the test case number 2 and I am also generating the EP wave after the run. So here it generates the waveform, and now our test case 2 was read operations. So first of all, here the writing of the data is done. So here write enable signal is enabled, and at the positive edge of the clock the data is written and the empty flag becomes 0. As soon as the data is written in the FIFO, empty flag sets low. After that, the read enable signal is set high. So when the read enable signal is high, at the next positive edge of the clock, the data that was written in the FIFO is read out and it is stored in the data out. So it properly reads the data. So here on providing the write enable signal, the data is written in the FIFO and the empty flag sets low, and on providing the read enable signal, the data is read out from the FIFO, and again the empty flag is set high. So it is clearly verified from the waveform. Similarly, we could verify the other test cases by generating the waveforms. Now I am going to explain the various waveform snaps which are taken from the Vivado simulator. So my first test case is write operation. As we can see from the waveform that when the write enable signal is set high, the data is written at the next positive edge of the clock and the empty flag sets low, which indicates that our data is properly written in the FIFO and setting the empty flag properly. Now we are verifying the read operation test case. Here, first of all, data is written in the FIFO. So first of all, the write enable signal is set high, and in the next positive edge of the clock, data is written in the FIFO. Now here, read enable signal is high, and in the next positive edge of the clock, data is read out from the FIFO. So here, first of all, when the data is written in the FIFO, the empty flag sets low in the next positive edge of the clock, which indicates that the data correctly writes in the FIFO. And when the read enable signal is set high, then in the next positive edge of the clock, the data is read out from the FIFO, and then again the empty flag sets high, which indicates that our read operation is done correctly from the FIFO, and FIFO again get emptied after the read operation. Next one is full condition. Here the multiple data are written in the FIFO up to the FIFO depth, and when the number of data items is equal to the FIFO depth, the full flag sets high, which indicates that no further write operation can be done. Similarly, empty conditions. Here we are writing the multiple data, and after that we are reading it. When all the data are read out from the FIFO, the empty flag sets high. Next one is single element write read. Here we are writing the single element, after that we are assessing it. Next is multiple lines. Similar to full condition, we are writing multiple data, and after when the number of data is equal to the FIFO depth, full flag is set high. Next is multiple read. We are writing multiple data first, after that we are reading it, and when all the data are read out, the empty flag is set high. Next one is reset functionality. Here we will verify the reset functionality. When the reset signal is set low, the empty flag is set high, which indicates that the FIFO is correctly initialized. Here we have used asynchronous reset in our design, so the empty flag sets high as soon as the reset is set low. We have used active low reset signal, and it does not wait for the clock as it is asynchronous reset. Next one is wraparound conditions. Here we have written the multiple data. After that we are reading few data, and again we are writing. Now when the whole data is read out from the FIFO, then the last data that we have written also get read, which indicates that the wraparound test case is passed. That is, FIFO wraps when the write pointer and read pointer reaches the end, and it resets to 0. Next one is simultaneous write and read. Here both the write enable and read enable signals are set high simultaneously, and then the writing and read operations is done. So here as we can say that the writing and reading is performed when the both write and read enable signal is enabled, which indicates that the both pointers are updated properly, avoiding any race condition. Next one is overflow condition. We are writing the data beyond the FIFO depth, so it neglects it and correctly handles it. Now we are going to verify the underflow test case. Underflow occurs when we are trying to read from the FIFO when the FIFO is empty. Here the read enable signal is set high and also the FIFO is empty. So in that case the FIFO should correctly output the previous stored data, indicating that the underflow test case is passed. This project successfully implements and verifies synchronous FIFO using Verilog, ensuring its correctness through an automated test bench, covering adaptable design with stable operations. The FIFO design efficiently manages sequential data storage and retrieval, making it a critical component in digital system for buffering and synchronization. The project not only strengthens our understanding of FIFO architecture and test bench automation, but also provides a solid foundation for future enhancements. So that's all from my side. Thank you for your time and attention.